Okay, welcome after yet another long break. Uh, this was unforeseen. Okay, so so today we'll be looking at some applications of epsilon bias spaces. In fact, what I'm going to be doing is I'm actually going to only be doing one application, but in some sense, it holds within itself a lot of the details that show up in other applications, etc. Because to do many of the other applications, one needs to go a little deeper into Fourier analysis, which would be a bit of a sidetrack for this course, which is why I'm not going to do this. But we will look at one specific application and see how we can solve the problem using epsilon bias spaces. So let me do a very brief recap. We started this journey because we wanted to understand this concept of pseudorandom generators. And to understand pseudorandom generators, you first needed a notion of something called computational indistinguishability. And what was computational indistinguishability? It is roughly saying that you have a certain class of tests that you care about. And let's say this is some class of test C. And typically these tests are thought of as, for every input, it assigns a number between -1 and 1. So think of it as some value that is assigned to every input. And you want to know what is the expected behavior of such tests on two different distributions. You have two distributions, X and Y, on strings. And you want to know what is the expected behavior of the test when I draw a string according to distribution X versus I draw a string according to distribution Y. And if it so happens that every test in my class roughly behaves the same way, with respect to these two random variables X and Y, we will say that the distributions X and Y are epsilon computationally indistinguishable for this class of tests. And the most general thing that we'll eventually want to say is that this class of test is going to be anything that is computable by a small circuit. Like to make it as general as possible, because we eventually want to fool a randomized algorithm that runs in polynomial time. That's the eventual goal. But this definition is useful because you can sort of now start making baby steps. Like start with very simple classes of tests, see if you can fool them, and slowly build up your toolkit in order to be able to fool more complicated tasks. And once you have a notion of computational indistinguishability, you can now define what pseudorandom generators are. A pseudorandom generator is a specific way to define a distribution on n-length strings. And it is given by a map that stretches d bits into m bits. And now you just imagine your random variable to be, you draw the d bits at random and look at the resulting distribution that you get on n bits. Okay, so that is one distribution. And we want to say that this is an epsilon pseudorandom generator against a class C, or we sometimes say that this epsilon fools a class C, to mean that this, whatever, induced distribution by the generator is computationally indistinguishable from the uniform distribution. Like as far as the tests in C are concerned, like random bits that are obtained via this generator, it just seems to behave like how it would on uniform random bits, and the tests are not able to really tell the two distributions apart. Okay, so that's what this was supposed to be. And we specifically looked at one special class of tests. Yes.
So if we say that this computational indistinguishability is for all functions, then it is
statistical total variation distance. This is exactly total variation distance.
And then the G will be some sort of a hash function or something.
So in total variation distance, I mean, like it has to be something such that.
Yeah, not quite a hash, but.
Yeah, it needs to.
Whatever correlation we want in your.
Yeah, but basically, I think there won't be any reasonable pseudorandom generator where B is smaller than N. If you want to fight against all possible tests, I mean, like for example, if B is smaller than N, there is some string that you're going to miss out.
Yeah.
So your test could just be like, is the string going to come up or some such thing like that. So that's the reason why, in general, if you have total variation distance, you won't be able to come up with anything significantly better than N. You might maybe shave off some constant number of bits because you are allowed to be epsilon close or something, but you won't be able to do anything significantly better. Okay. Okay. And last time we did a bunch of other things. We also showed that it is possible that there are pseudorandom generators against poly-size circuits where D was something like order log n. So in some sense that there are lots of hay in the haystack. We are trying to find one explicit construction, but of course the argument we had last time was just a counting argument basically. But right now let's focus on something for which we do know how to build pseudo-random generators. And one of the simplest classes, which is already super powerful, is just this class of linear tests. Okay. The set of tests are just the following. You choose a subset of bits and compute the parity of those bits. And they're called linear tests because if you imagine working over the field F2, you are like computing a linear function on n bits. Okay. And so the test TS is it just takes a string of length, an n-length string, and just returns the parity of the indices that come from this window S. Okay. And we'll say that, last time we came up with this notion of epsilon bias distributions to mean these are distributions on 0, 1 to the n that actually fool such linear tests. And we constructed one such distribution last time, which I will briefly now describe what the distribution was. Okay, and these are called epsilon bias distributions, or if you think of just the sample space, I'm assuming that, the reason it's sometimes useful to think of distributions versus the underlying set of strings is that the distribution could assign slightly different masses on those strings. Okay, it's just a slightly more general way of thinking about it. And let me first, before we go into this, I'll maybe give a sense of why is it called epsilon biased. Okay, so let's fix any non-empty set that you care about. Saying that it's epsilon biased is basically translating to this question. So if I gave it the uniform distribution, the probability that this was equal to 0 should be half for a non-empty set. But for an epsilon bias space, because it's supposed to epsilon fool what is happening, that will basically say that the probability has to be very close to half. It must be like within like an epsilon length window around half. That's what this is saying. Okay. And there is a standard name for this, which is like you somehow say that the bias of this random variable under the current distribution, under the distribution X, you'll say this is where this bias just refers to the following. So probability that whatever this random variable is Y is equal to 0 minus probability that Y is equal to 1. That's what bias of Y means. Okay, it's a shorthand for this thing. And so this is like saying that you want the bias of every parity to be very small. And that's why it's called an epsilon bias space or a small bias space, and so on.
So the definition of having a PRG for these linear tests, that would give us that the probability of this XOR over all xi belongs to X.
So whatever is the probability of this with the uniform distribution, I want it to be within epsilon of the other thing. Okay, maybe I'm losing out a factor of 2 or something like that.
But this small detail that I thought it would just be 1 minus epsilon into 1 plus epsilon. It's supposed to be 0.
So the point is that the test is also allowed to do something like if it takes value 0, I'm going to take plus 1. If it takes value 1, I'm going to take minus 1. In that case, if I plug in the uniform distribution, I get 0. But if I plug in an epsilon bias distribution, I'll get epsilon. If I plug in this distribution, suppose the value was actually 1 minus epsilon by 2 and 1 plus epsilon by 2, the expectation will turn out to be epsilon because it's...
Oh, okay.
So that's the reason why...
Okay.
Okay, so this is what bias means. Don't worry too much about the constant thing. Okay, so obviously if S was empty, then the parity by definition is always 0. Well, that is true irrespective of what distribution you have. There's nothing interesting going on there. But for non-empty sets, we know that the uniform distribution is supposed to be completely unbiased, and we want our distribution to roughly have that property. Okay, and last time we saw this construction of Alon, Goldreich, Hastad, and Peralta, which roughly went like the following. You choose an extension field. You choose an extension field of F2 whose size is like n over epsilon. Okay, and the distribution is going to be obtained like I'll pick up 2 elements of this large extension field, A comma B, And using A comma B, I will generate an n-length binary string. Well, what is it going to be? You basically want to look at A par 0, A par 1, A par 2, all the way to A par n-1, powers of this field element A. But these field elements are like n-length vectors, not L-length vectors. So you just take the inner product with B at every step. Okay, so that it becomes a bit. Okay, and that's what the AGHP generator is. So in terms of the seed length that is used, you just need to pick two random bits from this field F. Sorry, two random elements from this field F, and that therefore takes twice log of n over epsilon. That's the seed length. Okay, and it returns n bits. And we basically last time showed that this distribution was actually epsilon biased. And this used a key observation, which is that if you have a non-zero vector, and if you pick a vector B at random and look at the inner product of this fixed non-zero vector with B, that is a uniformly random bit, which is like going to 0 or 1. So we basically just did the following. We said that, well, let's look at one such parity. Okay, which looks like parity of some, maybe with respect to some window I. Okay. And because of the way my bits are constructed, you can think of the function fs to be equal to summation x bar I, where I is an s. Just imagine this polynomial. Okay. And what we will get when we take the parity of those s bits is basically the same as you are evaluating this univariate polynomial at the point A and taking an inner product with B. Just because inner products sort of distribute over the sum. Okay. And now it's a simple, this thing is that, no, the main observation that we had last time was that if somehow it so happens that this fs of A was non-zero, this is truly unbiased. Like it will be a uniformly random bit between 0 and 1. So which means whatever bias you have can really come only from the fact that, maybe you chose an A such that this fs became 0. But fortunately, fs is a polynomial of degree at most n, whereas my field consists of n over epsilon points. So the chance of me picking up an A such that fs is equal to 0 is at most epsilon. Because I have a lot more elements in my field than the number of roots that f can have. So which means this is the probability that you have it's a convex combination of something that is potentially unbiased and something that's completely biased. And the unbiased part is only taking weight epsilon. Okay, and so this is going to tell you that the final random variable that you have is going to have, it's going to be, the probability of it being 0 is going to be within half plus epsilon and half minus epsilon. Okay, it's a fairly simple argument, but it just takes a little bit of time to get used to it. It's a fairly short argument. Okay, so this was the AGHP construction that we saw last time. It's not the best construction of epsilon bias spaces, but for our case, 2 log n over epsilon is awesome. We can ask for more, but we don't need to.
What more can we ask for?
So, turns out the right answer is log n plus 2 log 1 over epsilon.
Oh, I see.
Okay, that should be the right answer. And we know how to get very, very close to this by the recent constructions of unknown Tashma. But this one, the constant on the log n is instead of 1, it is 2. So if you think in terms of sample space, there exists epsilon bias spaces where the number of strings is just n by epsilon squared. But this is instead n squared by epsilon squared. Because I have to pick A and B from this field. So there are n by epsilon the whole square. But we at the moment, we don't care about this. Okay. So the thing was, we only need 2 log n over epsilon random bits to construct such epsilon bias spaces. So this is roughly what we saw last time. And now we are going to start looking at some specific applications of this. And in fact, I'm going to give you just one application of this, which is this problem we're going to try and come up with better and better solutions for. It's a notion of something called K universal sets. Actually, I don't know if this is a standard notation. I'm just going to define. This is how I saw it defined in some notes. I'm going to use this thing. So what is a K universal set? It's a collection of strings which have the following property. If you choose any window of size K, and just drop all the strings besides those indices, you should be able to see all 2 power k strings. All the patterns possible must be visible here.
Otherwise, there is this function called shattering. So it shatters every subset X.
Isn't it the
Oh, this is just VC dimension?
No. It's not.
This is not VC dimension.
Because he's saying that every universal set and those sets are different. Because this is basically, it shatters every subset. Yeah, the VC dimension is the largest subset which you shatter. Yeah.
Oh, VC dimension is the existence of one window that you shatter. Whereas this one is saying that I want every window of length k to see all possible patterns. Okay. So that's what k universality means. And obviously the question that we would want to know is how small a W can I choose while it being k universal? No, obviously I can choose W to be the set of all strings. That will work. But we don't want to do that. We want to do something better. So can you think of choices of W's that will work?
K is given already, right? K,
Okay, let's think of k as, I don't know, 10. Okay.
yeah.
I'm just trying to think of the most stupid things first. Like k is equal to 1 is basically you just take
All zeros and all ones.
Sounds
Yeah, that's right. That works. So if k is equal to 2, what can you do?
So certainly for if I just run the disjoint string, then by 2 things, you need to take all the like,
Sorry, I didn't understand. What do you?
if I'm trying to see which string do I need to include, I should certainly be including.
I think you people are overthinking this.
And for K equal to 2, you can take.
I mean, what do you want? You want on every. I mean, if I fix to a window of size 2,
There should be string.
I want to see 0, 0, 1, 0, 0, 1, and 1, 1. What does this remind you of? No.
What
does this remind you of? On every window, I want these 4 things to show up. If I want 2 universal. It's one of the first things that we did.
Oh, I mean, it's just some independence.
Yeah, exactly. If you use k-wise independence, of course this will be true.
Yeah.
In fact, k-wise independence says something far stronger, right? It says that if you fix a window, the number of patterns you see of every k-length string is going to be equal. That's what k-wise independence says. This one is not asking for that. It's just saying that I want every such pattern to show up. I'm not really keen on it being exactly the same. So certainly one thing that will work is that if you choose a k-wise independent distribution, that will definitely work. So at the moment, we know that we can always make size of W at most. I think the k-wise independent distribution had something that looked like n to the order k, or n to the 2k or some such thing like that. So that's basically what we at the moment know how to achieve. Okay. So we know how to do this just using k-wise independent. But it would be nice, for instance, if I can construct k universal sets where k is something like log n, where the size is still polynomial in the parameter n. Okay. So there are lots of applications where this k universal thing just shows up. So one of the things that's going to happen today is that we are going to try and come up with better and better constructions of k universal sets.
So for pairwise independent hash functions, we had n square.
For pairwise alone, we had n actually. Somehow there we were a little careful, but I think if you in general make it k-wise independent, you get something like n to the k. I don't exactly recall what the amount is.
But wait, did we see that is the best you can do?
I don't think I gave it as a homework problem also, but I think it is true. I mean, it will be n, at least n to the k minus 1 is a lower one. You need n to the k minus 1 things. I think the best construction that we currently know is like maybe n to the 2k or maybe n to the k plus 1.
This is the VC dimension already will be.
Uh-huh.
If the VC dimension has this k,
yeah, then n to the k is the right.
You make a k is already a lower.
Yeah.
I think k-wise independence is a stronger notion than k.
K universal.
Here we expect to do.
Yeah. By the end of the lecture, you will have much better constructions of this. Okay. Okay, good. So, so basically, one of the things that I want to lead you to is the fact that let's go back to our k-wise independent, like upper bound for this. Now the point is, notice that since I'm only insisting that all the patterns should show up, look, I don't really need them to be k-wise independent. Suppose you told me that every pattern should, sorry.
No, I think there is some iterative way where you can just keep adding things and satisfy this.
Actually, if you have such a construction, that will be great. I mean, I would like to.
No, I just is it some iterative thing that you're.
It's a more general thing. Basically, what we are going to construct is instead the following. We're going to construct a distribution that's not really k-wise independent, but it's sort of close to k-wise independent in the sense that the following happens. What does k-wise independence tell you? It tells you that if you fix a certain pattern on a k-length window, the probability that you see this pattern is exactly 1 by 2 par k. But instead, suppose I told you that it's 1 by 2 par k minus a delta. And as long as delta is smaller than 1 by 2 par k, I just want this to be non-zero. So in some sense, even if you have a distribution that is sort of close to k-wise independent, that would also be good enough for this construction. So the first thing we are going to try and do is we basically ask, can we construct such a distribution? If I'm allowed some slack around 1 by 2 par k, can I significantly reduce the seed length? Okay. Now, in order to do this, I need a little bit of Fourier analysis. So
So do you have a way of doing this without invoking polynomials? Without fooling degree k polynomials?
Yeah. We'll just use epsilon by spaces.
No, full degree k polynomials also using epsilon by spaces.
Yeah, but we don't. Okay, I'm not going to use that analysis or something. This is going to be very elementary. This will be very elementary. Okay. So in order to do more about this, we need a little bit of Fourier analysis. So I'm going to tell you the bare minimum that's necessary. In fact, I'm going to tell you in a way that doesn't take too much of a basis change. Okay, because otherwise I'll have to really go to plus minus 1 and so on, which I'm not going to do. So this is just going to be Fourier analysis 101, just the bare minimum.
The k Fourier coefficient.
Yeah.
And that's it.
That's it. Yeah. Okay. Yeah. Okay. So here is the Fourier analysis 101. So the starting point of all of this is the following. Let's look at the set of all functions that are real valued now. Okay, I want it's a function on strings, but it returns a real number. Okay, and we're going to call that script f. So the first observation is that this actually forms a real vector space. Okay, and well, because if you have any two functions f and g, then af plus bg is also a function. So you can scale, you can add, it has all the properties that a vector space has. Okay, so the first question, what is the dimension of this space? Like how many independent functions do we have in this space?
I mean, you need to decide.
No, this is a number. So what is this number?
This n.
Okay, why is it n?
So you want to be able to represent every function as this is all set of all functions.
So just think of every function as a truth table.
Yeah, it's telling you.
Like it's basically a vector of length 2 to the n that's telling you what the value is. So therefore the dimension is like 2 to the n. Okay, and the standard basis is things like the following kind, which is these delta functions. That is, at a specific point x, you take value 1, everywhere else you take value 0. Okay, and if you like polynomials, you can write this delta function in this form. It's this specific polynomial. X is some fixed string, and you're just basically doing some minor manipulation. Okay, So this is the starting point. And as we did for when we did spectral graph theory and so on, where we were also talking about eigenvalues and stuff, one thing that you want to define the moment you have a vector space is an inner product that makes sense, that is convenient for you to work with. And an inner product that is super convenient here is just the same inner product that we had when we are dealing with graphs and stuff like that. And it's just this. You basically look at this is what's called the correlation of f and g. Okay, you pick an x at random and you look at the expected value of f of x times g of x. Okay. Now it turns out once you have this inner product, and of course, if you want to build a basis for your set of functions, in any such space, it always makes sense for you to take a constant function as one of your vectors in the basis, something that just takes one everywhere. And now you can ask, from the constant function, can I build a nice orthonormal basis? That is very useful. Okay, and there is a really, really useful orthonormal basis, which is defined by the parity functions. But here the parity function is the 1 minus 1 version of the parity function. You just think of it as minus 1 power the parity of xi. So the parity is 0, it takes value 1. If the parity is 1, it takes value minus 1. Okay, so this is a plus minus 1 version of the parity function. And let's just briefly see that the following is true, that in terms of this inner product, these parities form an orthonormal basis. So, okay, this is like sort of immediate. If s was equal to t, then minus 1 plus 1, once you square it, it's going to become 1. So the expectation is going to be 1. So there's nothing fancy going on here. So it suffices to just look at what happens when x is not equal to t. So what is chi s and chi t?
This expectation.
This expectation is over the uniform distribution on all strings. Okay. So this is going to be minus 1 power. I take the parity with respect to s. And then I need to add the parity with respect to t. Okay. So which means indices that were present in both s and t get added twice. So it contributes minus 1 squared, which is 1. And things that are not there are not there. So this is the same thing as the expected value of minus 1 power the parity with respect to the symmetric difference. That is things that are in exactly one of the two sets. And here you just use the fact that as long as you're looking at picking an x uniformly at random, and as long as this set is non-empty, there are going to be equal number of things that have parity 0 and parity 1. So they're going to contribute an equal number of 1s and minus 1s, which is equal to 0. Okay. So great. So it tells us that, here is a nice basis that you're going to be working with. And this implies that any function you care about can be uniquely written as a linear combination of this basis vectors. Okay. And the coefficients that show up in such a representation are what are called Fourier coefficients. Okay, f hat s is refers to what is the coefficient that chi s comes with. Okay, and it just so happens basically the entirety of Fourier analysis is that there is a lot of information that is hidden in f hat s, which you can analytically work with. I mean, it's a much more useful basis to work with than the standard monomial basis. Okay, so now the next question we might want to ask is the following. Suppose I give you a function x and I ask you, can you compute what f hat of s is going to be? Okay, so how do we compute f hat of s? So this is the advantage of having an orthonormal basis, because I can always write f as summation f hat s chi s. Okay, let me use a different letter. F hat t chi t. Which means if I want to extract out just exactly what f hat s is, one thing I can do is I can just take the inner product of f with chi s. And this is going to be summation f hat t of chi t with chi s. And everything cancels out except f hat of s. So basically, if you want a particular coefficient, just take an inner product with the corresponding vector. And that's what you end up with. So, okay. So another advantage, because it's an orthonormal basis, is that the inner product and the standard inner product you are looking at is just going to be the inner product in terms of the Fourier coefficients. You think of the Fourier coefficients as a vector and take the standard dot product that you would take. Okay. And a special case of this is like what happens when you take the inner product of f with itself. And that's going to be summation f hat squared, just by the above definition. And there are two special cases that are quite instructive. The first one is if f happens to be a Boolean function, Boolean valued function, the sense that it takes values which are also 0 and 1. Notice the inner product of f and f is the expectation of f of x. And f takes values only between 0 and 1. So which means its expectation is basically going to be the probability with which it takes value 1. And therefore, you know that it's going to be at most equal to 1. Okay, and another special case, which is also very useful, is when if f takes values only -1 or +1, then f squared is always going to be equal to 1. So the expected value will always be equal to 1. So in that case, you get that summation f hat s squared is exactly equal to 1. And this is also called Parseval's identity. Okay, but we won't need much of this here. But let's go back to the regime that we will be dealing with. We'll be dealing with functions which are actually distributions. Okay, what I mean by that is for every string, it is just going to, the value associated with it is the probability with which this string shows up in the distribution. Okay, so that's the function d. When d is a distribution, I'm going to interpret d as a function in this form. So I want to know, okay, let's first ask ourselves, what is d hat of phi going to be? So by definition, it's just the expectation, it's the correlation of f with the constant function. Right? So this is going to be the expected value of d of x with the constant function 1. And what is this? So you have to sum up probability. So the probability of choosing x is 1 by 2 power n. I need to multiply that with d of x and add up over all possible x's. But once I add up d of x over all possible x's, I'll get 1. So you end up with just 1 by 2 power n. So for every probability distribution, the empty Fourier coefficient is just 1 by 2 power. So, like for example, the uniform distribution is just 1 by 2 power n everywhere. So it's 1 by 2 power n times the constant function. Okay, now the next question is, what is d hat of s for a non-empty s? Okay, let's look at this. So d hat of s, this is the expected value of d of x with pi s of x. So there are some strings where this is going to be equal to +1. There are some strings where this is going to be equal to -1. So if you expand this out, what you end up getting is just the following. There's the probability when you draw x according to d that d of x is equal to 0. The parity of I and s of x is equal to 0 minus the probability when you draw x according to d that the parity of I and s equal to 1. Basically, because if you expand this out, you're going to add up all those strings that contribute, that have parity 0. You're going to add up the total mass according to d. That will come up with a +1. But if the parity was 1, then it will come up with a -1. So that's what, that's what these two distributions are. Right? And what is this? This is basically what we defined earlier. This is just the bias according to the distribution d of whatever, this function. Okay. I should have written it above, I guess. Anyway. Okay, this is what the bias that we are talking about. Which means that saying that you want your distribution to be epsilon biased is exactly the same as saying that I want all of the non-zero Fourier coefficients or non-empty Fourier coefficients to be at most epsilon. Okay, it's an if and only if. So this gives a completely Fourier analytic way of just looking at what is epsilon bias spaces in terms. I think my iPad lost connection. Hopefully we are back and hopefully the stream is still going. I have no idea if the stream is still going, but I mean YOLO. Okay. Okay. So for the uniform distribution, let's look at what these Fourier coefficients are. Now, obviously, for the empty Fourier coefficient, it's going to be 1 over 2 pi because any distribution has this problem. But the uniform distribution is going to ask again, what is this minus this? So it's basically the other Fourier coefficients are the bias of the corresponding parities. And those are exactly equal to 0. Which is not surprising because how do you write the uniform distribution? It's 1 by 2 power n times the constant function. And that's the unique representation. So everything else is 0. Okay. And here is a really beautiful lemma. By the way, this is called the Vazirani XOR Lemma. It says that any small bias distribution is actually reasonably close to the uniform distribution in terms of statistical distance. But that reasonably is with a big pinch of salt because there is a factor of 2 power n by 2 that is sticking in front of it. Okay? Huh? This is very, very tricky. Oh, okay. Okay, and let's see how the proof is. And the proof is like super simple. Well, let's pick up an arbitrary statistical test. Okay, which is like t from 0,1 to the n to 0,1. In fact, you can make it -1 + 1 if you want. We don't care. And I'm just going to write this test in terms of its Fourier basis. Some t hat of s times chi s, chi s of z. That's what this is going to be. And let's just look at the thing that we care about and let's write that down in terms, I want to know how well does a test distinguish between the distribution D I care about and the uniform distribution. Okay. And what is the difference that we need to look at? We need to look at expectation of T of Z when I draw Z according to the distribution D versus expectation of T of Z when I draw Z according to the distribution U. And just the T of Z, I have replaced it with this sum. Okay. And if you move things around a little bit, what you end up with is this. That is, let's just swap the sum and the expectation. So it's going to be summation over all S of T hat S. And inside that is the expectation of chi Z when Z is drawn according to D, and whatever chi Z when Z is drawn according to U. Now, when S is empty, this is equal to 1 by 2 power n, this is equal to 1 by 2 power n, so it cancels off. When S is non-empty, because it's an epsilon bias space, this is at most epsilon, this is equal to 0. Okay, so therefore, what you end up with is like this is at most, in fact, epsilon times summation, the absolute value of T hat of S. Okay. And at the moment, I don't know how to bound absolute value of T hat of S, just adding up all the Fourier coefficients. But I do know how to bound the sum of the squares of these things. So let's get to that using a Cauchy-Schwarz, because I'll write this as this times 1, and which is at most epsilon times square root of summation T hat S